Okay, we want to begin a quick discussion of vectors. Start with displacement vectors. If I have the point 25, the point 16, 14, the point 22, negative 2 in the xy plane, I can summarize the nature of the displacement from this point to this point by an arrow that goes from here to here. Initial point 25, terminal point 16, 14. I'm going to write down a little terminology. Okay, I call this vector A. This vector is represented by an arrow that starts here, ends here. We call this the initial point. The initial point is 25, and the terminal point here is 16, 14. We say that the vector A will take us from the point 25 to the point 16, 14. Now, question. The same vector A will take us from the point 39, 30, 9 to some other point. So if I draw vector A, it's the same vector, it's got the same length and the same angle as measured, let's say, with the positive horizontal axis. So it's got the same length and same direction. So right, same length, same direction as here, and that should be implicit. Then at what point do we end up? Okay, we have two coordinates here. Now, if you're familiar with vectors, you probably already answered this, but let's see how else we could move through this displacement. We could move in the horizontal direction and then in the vertical direction. So we would have something very much like a run and a rise. Matter of fact, if we wanted the slope of the line in the direction of this vector, we would divide this rise by this run. Well, we know that this run is 16 minus 2, which is 14, and this rise is 14 minus 5, which is 9. Now, if this vector, this arrow, has the same direction and the same length as this one, it follows very clearly that we have the same run and the same rise. And if we run 14 units from here, we're going to end up at coordinate x coordinate 44. And if we rise 9 units above 9, we end up at x coordinate 18. So our answer to our question is we end up at 44, 18. So we denote the vector A by the ordered pair 14, 9 with an arrow over the top of it to indicate that it's a vector. It's not a point in the plane, it's a vector, and that vector can apply to any initial point in the plane. So any initial point at all, any point at all. If we take a point here, we draw a vector of the same length and magnitude, same length and direction, and we'll get a terminal point that corresponds to the initial point with a displacement equal to this vector between the 2 points. Okay, so what's the vector B from the point 16, 14 to the point 22, negative 2? Well, you should pause and do that yourself. It's what? The x component of that vector is 22 minus 16. That would be the run if we go from 16 to 22. Okay, so if we do this displacement vector, I don't want to not interfere with my labeling here. It badly Let me reposition my label there so we can move on without obstruction. Okay, I've relabeled the 16, 14 up here. Now, the run from here to here is 22 minus 16, which of course is 6. So we could write 22 minus 16 equals 6 to get the run, and negative 2 minus 14, which is negative 16, to get the rise. So that's negative 2 minus 14, and we put an arrow over it, and we say that that's equal then to the vector 6, negative 16. This vector also could apply any place in the plane, and we'll call this vector B. Now, we've got a vector displacement from from the first point to the second, and from the second point to the third. How about a vector from the first point to the third? Okay, that would be this vector. What would the coordinates of this vector be? There are actually two ways to calculate it given the information we now have. Okay, well, to find the components of the vector, just using a geometric picture, we've got to find the rise here and the run here in this direction. So we've got to find the rise this way and the run this way. So how are we going to calculate that? Well, the way that imitates what we've done here. So we could say vector C, let's go ahead and label this vector C, is 22 minus 2, that's the run, and negative 2 minus 5 is the rise, so the vector is 20, negative 7. So that's straightforward. That just imitates what we did. There's another way to do it. Can you see what that might be? Okay, well, look at this picture. We've got a run of 14 from here to here and a run of 6 from here to here. This run has to equal the total of these two because these lines, these vertical lines, are all parallel, or supposed to be. I didn't draw them all that well, but you know, you have a parallel here, a parallel here, a parallel here. The distance from here to here is 14. Distance from this parallel to this parallel is 6. They add up to 20, and that's the distance between this parallel and this parallel, which is the run. So we could write this as 14 plus 6 is 20. And the rise, well, again, we have parallels here and here, so distance here is 6. Well, the displacement, because we're moving from here to here, displacement here is and I'm not saying that right. We got a displacement of plus 9 from here to here, and then minus 16 from here to here. Okay, so that the rise is 9 minus 16, which is negative 7. And of course, these don't add. This displacement is upward, this displacement is downward. So the distances here don't add, but the displacements do. Okay, so we have a displacement of 9 and then a displacement of negative 16, giving us a displacement of 9 plus a displacement of negative 16. It gives us 9 minus 16 equals negative 7. So if we add the horizontal displacements, 14 and 6, we get the horizontal displacement here. If we add the vertical displacements, we get 9 and negative 16, which is negative 7 here. Now, an alternative calculation is just to use the points. That's what we did down here. The other way to say it then is, of course, 22 minus 2 equals 20. And over here, we have negative 2 minus 5 equals negative 7. Either way of calculating it would be correct. Okay, now starting then from 2, 5, our displacement vector A takes us to a point, and then we follow from that point by displacement B, and that combination of displacements takes us to the point 22, negative 2. Now, starting again from 2, 5, displacement C alone takes us to the point 22, negative 2. Okay, now we're going to call the displacement A followed by displacement B. We're going to call that A plus B. So A plus B takes us from 2, 5 to 22, negative 2. And the idea that we're adding the two vectors if we do this. If we start somewhere and do the first displacement, and then from that point we do the second displacement. The net displacement we're going to call A plus B. We're going to call that, excuse me, addition of displacement vectors. Well, what can we say then about A plus B in this figure? Well, it's clear that A plus B is a vector that takes us from here to here, and C is a vector that takes us from here to here. So we're going to conclude that C equals A plus B. So we state that here and surrounded by red. Okay, A plus B has the same effect as C, so we say that C is equal to A plus B. The displacement vector C has the same effect as the displacement vector A plus the displacement vector B. And now it's clear that we can calculate A plus B by simply taking the ordered pair 14, 9 with the arrow over it to indicate it's a vector, and 6, negative 16, again with an arrow over it. And we add the 14 and the 6, and it should be clear from the picture why we add the 14 and the 6. And then 9 minus 16, 9 and minus 16. And it should be clear why we do the 9 and the negative 16. And that gives us 20, negative 7, as was indicated here. So the calculation we show here just summarizes what we observe here about the picture. So to summarize, when we apply a displacement vector starting at some initial point, go to terminal point, we can apply that same vector to any other initial point. Now, if we start at some initial point, apply a vector to get a terminal point, and then use that point as the initial point for the application of another vector, the result gets the point that we end up at is the same point we would end up at if we started here and ended here by some vector, by some displacement vector C, and that vector C is the sum of the vectors A and B, and is calculated this way. And I've indicated that over here by saying that this A plus B gives us this vector, and that's equal then to the C vector.